Right, so this video is about L'Hopital's rule. You can also see an S in there and it reads kind of like L'Hospital, although it's still L'Hopital. And it's another way for determining limits. So let's have a look. It seems like quite an intricate rule, but when we do examples, you'll see that it's actually quite a basic idea as it's applied in AP Maths. So let's have a look at L'Hopital's rule. There's a few preconditions, which I've written here in blue. So this is what the rule states. If n is a number, so we're assuming n is any particular number, so an example would use an actual number. Then the other precondition is if two functions, f of x and g of x, are differentiable. So in other words, I can find the derivative of f of x and I can find the derivative of g of x. Also, it's important that g of x may not be equal to 0 for all the x's on some interval. So whatever x I plug in there in a given interval, I can't get g of x to be 0. Then, other preconditions. If the limit as x tends towards n of f of x is 0, and if the limit as x tends towards n of g of x is 0, then when we find the limit as x tends towards n of f of x over g of x, that limit exists or is infinite. So these are our preconditions. Now let's have a look what the theorem actually states. And this is the important part. It states that the limit when x tends towards n of f of x divided by g of x is actually equal to the limit as x tends towards n of the derivative of f divided by the derivative of g. So if I'm finding the limit of one function divided by the other function, if those preconditions are met, then it's actually equivalent to the limit of the derivative divided by the derivative. Let's have a look at a few more interesting pieces of information with regards to that rule. Firstly, the rule stays unchanged if I replace n as a number with n being infinity, positive infinity, negative infinity. So when I look back here, I don't have to say if n is a number, I could say if n is equal to infinity, or positive infinity, or negative infinity. We also have if limit of f of x as x tends towards n is 0, and limit g of x tends towards n is 0, is replaced by the limit as x tends towards n of my function f is infinity, and the other limit is infinity. So this rule still holds true if the limit of each of my functions is not 0, but if it is infinity. Now, L'Hopital's rule uses derivatives to help evaluate limits involving indeterminate forms. Now, indeterminate forms are when we get 0 over 0, or infinity over infinity, or infinity minus infinity, or 0 to the power of 0, or infinity to the power of 0, or 0 times infinity. Those are indeterminate forms. The ones you'll encounter mostly in AP are 0 over 0. Now, application or repeated application of this L'Hopital's rule often converts an indeterminate form, like 0 over 0, into a determinant form, so that we can find the limit. Now, you'll see that we've done L'Hopital's rule without a proof. The proof at the moment is beyond the scope of what you can cope with in AP. If you take maths at university level, you will do the proof of L'Hopital's rule, and you will use this rule a lot. It's a pretty useful rule. Now, it seems like a lot's gone on here. And you might be thinking, geez, wow, this is quite a tricky rule. Let's summarize it in a way that makes a bit more sense to us. So, L'Hopital's rule summarized. The rule says that the limit as x tends towards a number of a function divided by a function is equal to the limit as x tends towards that number of the derivatives of those functions, the derivative of each function separately, numerator and denominator, which when we're finding a limit, in a nice determinate form, we can sub that n in place of x. So that's equal to that. We can do that provided, it's very important, provided that when we sub an n into our original to get the limits, we actually end up getting 0 over 0. We're not taking into consideration all our indeterminate forms here, but we take into consideration the one which we deal with in AP Maths. So now let's go and apply it to an example. So this example says, evaluate the limit as x tends towards 2 of my f of x, my top function, divided by my bottom function. Now, we are allowed to use L'Hopital's rule if we land up with a 0 over 0 in indeterminate form. So let's check. If I take my 2 and I sub it into my numerator here, I will get 2 cubed minus 2 squared minus 2 minus 2. Check if we're going to land up getting 0. 2 cubed is 8 minus 4, which is 2 squared. 8 minus 4 is 4. Minus 2 is 2, minus 2 is 0. Yes, we get a 0 in our numerator. Let's check if we get a 0 in our denominator. We sub in 2 here. 2 cubed is 8. 3 times 2 squared, so it's 8 minus 12 plus 6, okay, minus 2 also gives us 0. So we can see here we have a case. Here we have a case. We have a case of 0 over 0. Because when we subbed in that 2, we got a 0 in the numerator and a 0 in the denominator. So what L'Hopital's rule allows us to do is it allows us to find the derivative of the numerator and the denominator and take the limits of that. So I've got the limit as x tends towards 2. I'm going to differentiate just my numerator at first, which gives me 3x squared minus 2x minus 1 minus 2. Oh, hello, hang on a second. Not minus 2. The derivative of negative 2 is 0. Then I'm going to find the derivative of the denominator, which is 3x squared minus 6x plus 3. Now check again what happens when we sub in 2. Because remember, when we find a limit, we must first just see if we can sub in that value. That's the easiest way to find a limit. So if I sub x to be 2, I'm going to get 3 times 4, which is 12, minus 2 times 2. So let's just make sure we're getting this. I've got 3 times 4, 12 minus 4 minus 1, which is 7. Okay, so my numerator gives me 7. So we already know we're not landing up with an indeterminate form. But let's check our denominator. 3 times 2 squared is 12 minus 6 times 2 is 12 plus 3. 12 minus 12 is 0, so we end up with 3. So what we get here, once we sub in, to actually find our limit, we're going to get 7 over 3. All I did there was I subbed in 2 to my numerator and denominator, and because I didn't get an indeterminate form, I know that I found my limit. So that's the application of L'Hopital's rule. Let's have a look at another example. Here we're finding the limit as x tends towards 0 of 2 sine 2x over 3x. Now we know what the limit of sine of something over the same thing is. We know that that's 1, so we could adapt this and use that rule. But I'm going to show you that we can do the same question using L'Hopital's rule. Let's first check if we have an indeterminate case. Let's sub in x to be 0. So I'm going to have 2 sine 2 times 0. That's 2 sine 0. Now you can use your calculator to help you. Remember to use radians. Sine 0 is 0. 2 times 0 is 0. Denominator, we make x to be 0. 3 times 0 is 0. So again, here we have a case of 0 of 0, an indeterminate form, which means, yay, I can use L'Hopital's rule. So we keep the limit as x tends towards 0, and we find the derivative of that numerator. Okay, so finding the derivative, my numerator uses the chain rule. My 2 stays there. The derivative of sine 2x is cos 2x. Then I go inside and I find the derivative of that inside function. The derivative of 2x is 2. Go to my denominator and find the derivative of the denominator. The derivative of 3x is 3. So what I can do when I find a limit is I can take out a constant. 2 times 2 gives me 4. I can take that out and I can take the 3 out. So I've got 4 over 3 because the constants don't impact my limit. Limit as x tends towards 0 of cos 2x. Now when I'm finding a limit, I can test it. Let's see what happens if I sub x to be 0. Then I've got cos of 2 times 0. And actually, let's write that out. I've got 4 over 3. The moment I sub in, I don't have to write the limits anymore because I'm actually finding the limit. Cos of 2 times 0 is cos 0, so let's pop that step in as well. Times by cos 0. Now, use your calculator, or use your special angles, or think of the graph. Cos 0 is 1. So I've actually got 4 over 3 times 1, which is 4 over 3. So this gives you another way to evaluate your limits with your trig functions, provided you get an indeterminate form 0 over 0.